Hello and welcome. This is the video for section 1.2 dealing with the properties of functions and learning some function vocabulary we will be using for the rest of the year. To start with, we have our basic definitions. And what I'd like for you to do is to go to page 86 in your textbook, section 1.2, and go through the first half of the page to find these definitions. We will talk about them in class and review them to make sure that you understand them fully. I will be using those definitions for the rest of this video, so please press pause right now, go through, find the information, write it down on your sheet, and then come back to listen to the rest of the video. Okay, so welcome back. And what we're going to do now is we're going to talk about function behavior. We'll start with the idea of continuity. Continuity deals with how the graph behaves throughout the graph. So we start by defining what does it mean to be continuous. In order to be continuous, the graph cannot come apart at any point. Or if you were to draw the graph, so if we look down here at the continuous graph, if you were to draw the graph, you could draw the graph without ever picking up your pen. You can draw the entire graph without having to pick up your pen. So now that we have a basic idea of what continuity is, or a continuous function is, we need to talk about when it is not continuous or when it is discontinuous. The first one that we will talk about is something called the infinite discontinuity. When there is a break, so at the break, the graph splits, and the graph goes to infinity or negative infinity. So let's look at this graph. An infinite discontinuity graph would be in two parts, and at our discontinuity point, we'll call it A, the graph does not touch, and it goes off to positive infinity and to negative infinity. The next type of discontinuity is called a removable discontinuity. Removable discontinuity is a graph with a hole in it. It is a regular graph, but instead of having it full everywhere, there is a hole in there. So at this point, again we'll call it A, the graph is undefined. Now sometimes with the removable discontinuity, we might have another point up higher, so that it is defined, it's just the main graph has a hole on it. We can see the hole right there. Lastly, something called a jump discontinuity. It looks like two graphs, and as we're going along in our graph, there is a jump in the function values. Now when I say function values, I'm really talking about the y values. So my graph will come along and it will stop, and it will jump either up or down and start again. And either of these will be, so we have again at A, we have a discontinuity. It breaks. We have to pick up our pen and start again. Now it may be defined, it might have two open holes or one closed hole and one open hole, depending on the graph. So that's continuity and discontinuity. Now we also need to talk about increasing and decreasing behavior, and this is very similar to the idea of slope. It's not slope. Slope is only for linear equations. But when we talk about increasing and decreasing behavior for other types of graphs, we talk about it on a set interval. So in any interval, if we have a positive change in x, so the x is going from, say, 1 to 4, so we're going left to right, that positive change results in a positive change in our f of x. So our graph would be similar to this. Draw a graph down here, and we can see on any interval that we have here that I can choose 2 points. So let me choose a point here. Let's call this lowercase a, and over here we'll call it a uppercase a. We see that as x increases, the y values also increase. So if I were to draw, and I'll do it in red here, a line through those 2 points, we would have a positive slope. But on this interval, anywhere in this interval here, it is always going to have that positive slope. That's why it's increasing. Now, if we're talking about decreasing, what do you think would be the difference? Well, we're still going to talk about a positive change in x. So as we're going from a, lowercase a, to capital A, but instead of it increasing, instead of having a positive change, we're going to have a negative change. So we can take our graph and really flip it upside down and see that at these 2 points with a positive change in x, so positive delta x, we'll have a negative change, oops, that's an a, that should be a delta, meaning change of f of x. So it will be going down. We will have a negative change. And again, if I draw a line as best I can through these 2 points, you can see that this is going to have a negative slope. And at any point on this graph, or in this interval, it will be going negatively. It will have a negative slope for any 2 points. The last one is a constant interval. Again, we'll talk about positive change in terms of x. But in this case, we've talked about positive change in f of x and negative change in f of x. Well, what's left? The last thing that we're left with is that there is no change, or what we also say a zero change in f of x. We see this in equations like y equals 2. Okay, it's a constant function. It is just a flat line. So if I pick my a and my a, capital A and lowercase a, I see that there is no change, that the slope of this line is 0. So far I've drawn increasing function, decreasing function, and a constant function, something that is always that type throughout the function. But we can actually have a combination. It does not need to just be one. So I can have a part that is decreasing, a section that is constant, and a section that is increasing. So we have at our specific locations, our specific spots, we'll call it A and A. Sometimes it is going to be decreasing, sometimes it will be constant, and sometimes it will be increasing. It's actually more interesting when you get things like that. It's really boring if it's only one or the other. We will be estimating when it is increasing, decreasing, or constant based on its graph. If it's given to you, you'll be estimating the points, or on a calculator we can estimate it. We can graph it on the graph from the calculator. The next thing we need to talk about is boundedness, like the idea of a boundary. Boundary. Okay, I can almost spell. Okay, bounded below. There is a number, b, that is less than or equal to every number in the range of f, or every number, all the y values. This number, well, it's called b, is called the lower bound. So let's talk about bounded below. So here we are. Bounded below, if I have absolute value function, and let's say this value is -4, I say that this is bounded below, and the lower bound equals -4. Bounded above, very similar. We'll use capital B in this case. That is greater than or equal to. Oh, that's it does not equal. I want to say equal to every number of the range in F. This number is called the upper bound. O-U-N-D. So if I have an upside down parabola, we see that, say that's my upper bound. Let's say it's 3. That 3 would be my upper bound. And if a function is bounded both above and below, I have a function that is called just overall bounded. You can see a function like this, and notice how we don't have arrowheads here. This is not a full, the domain is not all real numbers. But most of the time, a lot of times, we see unbounded with our function, that every number in the range is used. Again, we will be checking boundedness or estimating boundedness from its graph, just like we'll be doing with intervals. The next thing that we're going to talk about is extrema. Extrema deals with mins and max, extremes or maxima. So max and min we generally call extrema. So local or relative is a number that is greater than, okay, I'm having difficulty writing here. Let me just do this. So b is greater than or equal to all the range values or the y values on some interval. It's sort of a closing area, not the entire range, but just some of them. An absolute maximum where b is, I can just write greater than or equal to all the range values. Therefore, b is called the absolute max, or just maximum. If we just say it's the maximum, that just means it's greater than everything. We can have multiple relative and local maximums, but there can be none or one absolute maximum. Relative minimum is very similar, but in this case we're looking at less than or equal to all range values. If it is less than, if that value is less than or equal to all range values for the entire f of x, we call it the absolute minimum, or just the minimum. And we can see, oops, that was very quick. We can see for maximum we have two relative, and here's my absolute maximum. For minimum, we have a local min, but no absolute max. Local max here. Okay, we'll estimate local and absolute extrema from the function. Okay, I will pick this up in the next section and finish off this unit. Thank you.